Let's talk about limit and colimit. Recall their definitions. There are many examples correspondingly, and it's very easy to mix them up. Okay. So in category theory, a branch of mathematics, the abstract notion of limit captures these essential properties of universal construction, such as products, pullbacks, inverse limits. It's better to precise in which categories I define these things, although, okay, those products, pullbacks, and inverse limit, they are themselves universal, satisfying universal properties. Actually, in every category, if it satisfies universal property, that is called the product, and the pullback, the inverse limits of that category. Okay. The dual notion of a colimit generalizes constructions such as disjoint unions, direct sums, coproducts, push-out, and their limits. It's not always makes sense to say what is disjoint union, an arbitrary category. I mean, here I think you should precise here this is for topological space or for category of sets, direct sum or in groups, or it's better to precise the category. I mean, limits and colimits, like the strongly related notion of universal properties and adjoint functors, exist at a high level of abstraction. In order to understand them, it's helpful to first study the specific examples. So let's look at the definition. First, we define what we call the diagram. Limits and colimits in category C are defined by means of diagrams in C. Formally, a diagram of shape J in C is a functor from J to C. So we have a functor from J to C. J is a category, and C is the category we want to define our limits and colimits. Okay. The category J is thought of as an index category. And the diagram F. So actually, this is called diagram. This is a functor called diagram. The diagram F is thought of as indexing a collection of objects and morphisms in C patterned on J. One is most often interested in the case where the category J is a small category or a finite category. As corresponding diagram are called a small diagram or finite diagram. So let's quickly recall what is called a small category and finite category. A category C is called small if both its objects and the home set are actually sets, not proper classes. I mean the collection of all the objects, the collection of all the home is a set. A finite category is a category simply saying of a finite set of objects and a finite set of morphisms. Let's say the definition of limit, that F from J to C be a diagram of shape J in a category C. So as we just said, it's just a functor from J to C. C is our category we will want to define what is called limit. A cone to F is an object N of C together with a family of morphisms indexed by objects X of J. Got functor from J to C, and for objects, let me simply write this X J. A cone is an object N of C together with a family of morphisms by the object X of J. So Cx from N to Fx together with object N C gives what is called a cone. Such that something to satisfy for every morphism in J we require that this collection of morphisms satisfies community diagram, which is shown. This is requiring here, so there is residual n, and then for any fx, fy, this diagram commutes c0 cx cy. This is your cone. This is it. When you apply your diagram, apply your functor f. So this is something happen totally in C. Objects of C and diagram commutes. Okay. This is the definition of a cone. And then let's say what is the definition of a limit? Limit of the diagram is firstly a cone, such that for every other cone we satisfy the universal property, which is any other cone factors through over n. And always make sure the correct direction. So here the important thing is this is the direction. There exists a unique map such that n factors through L. So this is the universal property. This is the object that satisfies universal property, and L is called the limit. Let's see that the cone factor through the cone is unique factorization. Okay, usually the way I remember this is when you draw a diagram. So firstly you have your cone, and then for arbitrary objects you always put it further. I understand what I mean. You not put it here, you put it further, and then satisfy the same thing, and then factor through you. Factor through you means to start from here, arrive in fx, you have to first go to L and then go to fx. Okay, we will see. So this way of remember things still works for colimit. Okay, so basically this is the definition. Limits are also referred to as universal cones. That's their characterizing the universal property. As with every universal property, the above definition describes a balanced state of generality. The limit object L has to be general enough to allow all other cones to factor through it. This is the philosophy of defined objectives in universal property, which means the thing satisfying universal property should be something very general enough to allow any other cone to factor through it. On the other hand, L has to be sufficiently specific so that only one such factorization is possible for every cone. Limits may also be characterized as terminal objects in the category of cones to F. It is possible that a diagram does not have a limit at all. Yes. However, if the diagram does have a limit, then it is essentially unique up to isomorphism. Okay, this anything that's a universal property is always unique up to isomorphism. So I can speak of the limit of that. Let's see correspondingly the definition of colimit. So firstly, what is called cocone? Cone is just general. Your diagram is still from G to C, but this morphism, family of morphism, change the direction. This morphism map into your object makes the diagram continuous, and then this n is called a cocon. More precise, this n together with the morphism is called cocon. And then now, the colimit is again the object satisfying universal property. So, which means firstly, let's say if alpha is called a colimit, if it satisfies firstly, you have your cocon, and then for arbitrary other cocon, you put it further. Okay, and then that factors through you, which means this time it's this direction. So you start from here to here, you factor through L. That's called factor through. Colimits are also referred to as universal cocons. They're characterized as initial objects in the category cocon, obviously. As with limits, if a diagram F has a colimit, then the colimit is unique up to isomorphism. Okay. So now let's say some examples of limits. Definition of limits is general enough to subsume several constructions used for in practical setting in the following. Consider the limit L5 of a diagram. So first example is terminal objects. If J is the empty category, there is only one diagram of shape J, the empty one, similarly to the empty function in set theory. A cone to the empty diagram is essentially just an object of C. The limit of F is any object that is unique factored through by every other object. This is just the definition of terminal object. So we're talking about examples, we're talking about particular categories J. And of course, you could also precise what is your category C, but if what you define, for example, the things here are general enough, if it's defined for whatever categories, just precise what is your J. So this example is telling that if J is empty category, then just recall is the definition of your limits. It means if you're an empty category, there is not at all morphism. And so what is a diagram? And what is a cone? So there is only one diagram, the empty one. And so what is a cone? Corresponding to empty diagram. And that would be firstly an object of C, and secondly with maps from it. It should be something like this, right? Cx, cy, but there is no cx, no cy. There is nothing, so it is equivalent to say there is just whatever object is a cone. And so when you say, remember we want to do this here, put arbitrary cone further, and it factor right through you. This is telling that for any object of C, let's say T, it has arrow pointing to you, so you are the terminal object. Okay. Similarly, products. J is a discrete category. The diagram F is essentially. Now, okay, pick another J, discrete category. The diagram F is essentially nothing but a family of objects indexed by J. The limit is called the product of these objects. So what is this? discrete category.